Color stylists often have a creative background in fields such as fashion design, interior design, or the traditional arts. They frequently use tools such as a mood board, shown here, or concept art, either hand-drawn or created in Photoshop. In this paper, we present color design tools created to mimic the design workflow used by color stylists. In computer graphics, there has been a long trend to represent material BRDFs to finer and finer precision with the goals of photorealistic rendering of the most subtle effects. A BRDF is a mathematical function representing appearance of materials across viewing and lighting angles. Most computer graphics systems that can render BRDFs are lacking a BRDF design interface, and those that do are often extremely difficult to design colors because of the staggering number of parameters available and unintuitive interfaces. As for material design interfaces, Lawrence created an interesting tool for designing spatially varying BRDFs by manipulating BRDF data plots. And Nagan approached BRDF selection using a variations or navigation approach. Other tools have tried to provide artistic design interfaces, but have largely missed the mark by providing control over the wrong parameters of the BRDF or the wrong interface. For example, BRDF Shop allowed the user to paint reflectance onto a spherical canvas, creating strange BRDFs with off-specular reflections. Although this interface has an artistic element, it didn't provide a useful interface for color designers. Our own initial attempt at creating an electronic system to help designers design and formulate new automotive paints was appropriate for chemists and color technologists. However, the technical interface didn't fully utilize the color stylist's unique creative skill set. We introduce a simplified BRDF appearance model based on color design terms well known in the industry. This model's primary components are the face, or near specular color, the flop, or off specular color, and travel, or color shift. In addition, a standard gloss term is included that represents the strength of the specular highlight. These terms combined together to create a second-degree polynomial plotting color through CIE-LAB space, indexed by the aspecular angle theta, the degrees from the mirrored reflection direction. Because of the low number of parameters, it is both easy to manipulate in real time and also see the changes of the BRDF update in the renderings in real time. This is crucial for interactive design. I'd like to note that we presented some of the same equations and also our initial BRDF system at CIC 11 in Scottsdale, and the new work in this paper directly builds off of that. Finally, this polynomial can be evaluated at various angles to get aspecular CIE-LAB measurements that correspond to paint standards. The paper reveals how to convert to and from each of the representations. But the important thing to understand is that the standard aspecular LAB measurements can be used to import physical color samples using off-the-shelf multi-angle spectrophotometers, and to export the color specifications using paint formulation systems. So even though our representation is simple, it is connected to physical reality. The parametric format is mostly an internal format for rendering, fitting, image processing, etc. Finally, the face, flop, travel, gloss model is useful in discussions about color and creating effective design interfaces. We demonstrate the usefulness of this simple model by creating 3 new color design systems. The first is a virtual mood board. A mood board is a collection of pictures, colors, materials, sketches, and other various visual artifacts that designers use to inspire and guide the process of designing new colors and new materials. The mood board on the left proposes a color treatment called hydrogen blue in the OC for a blue hydrogen-powered concept car inspired by the sporty trends of California's Orange County. And the right proposes a color called Orange Ball Paris for a young and fashionable audience. Our virtual mood board follows this concept, allowing an artist to put together collections of digital images and artwork and rearrange them on the mood board as desired. In addition, our virtual mood board allows an artist to use gathered images to design new colors. This is achieved by utilizing the face and flop color model. Eyedroppers representing the face and flop components can be placed on the mood board, and a newly designed color is generated in real time. This allows an artist to rapidly navigate through source material and design new and interesting color themes. Down in Texas, we call this the lasso mode because it wrangles up both face and flop color at the same time. This simple extension of the mood board replaces the dual eyedroppers with a single lasso that samples over a region under the cursor. It chooses the brightest pixels as the face color and the darkest pixels as the flop color. The second design system enables in-context tweaking. Designers often want to make minor adjustments to a color design. The image-based BRDF Tweaker is a color design system for tweaking color and appearance directly on an arbitrary 3D object. Using simple point-based lighting, we create a correspondence from image space to the BRDF. The BRDF is indexed using aspecular angle, which is encoded in an off-screen buffer. Another buffer encodes the reflected view vector. This information is used to create a draggable color adjustment widget that is context sensitive. As the widget moves across the surface of the object, the aspecular angle under the cursor is retrieved from the off-screen buffer. The BRDF is evaluated at that aspecular angle, and some basic color variations are computed. Surrounding the crosshair are buttons that show these variations, laid out like a woman's eyeshadow or makeup box. When one of these buttons is pressed, the BRDF is tweaked to reflect the variation at that angle. When the crosshair is dragged off the object, a different display is enabled. In this display, the aspecular angle is visualized like a topographic map with contour lines. In this mode, the artist can drag the dashed contour lines representing travel to adjust the rate of change between face and flop. Dragging the edge of the checkered circle representing specular highlight will adjust the level of gloss, affecting the size of the highlight. Here's a better view of the contour lines displayed over the evaluation surface. This illustration shows how specific aspecular angles in image space are correlated to positions on a graph of the BRDF. In this interface, artists can also move the light by clicking and dragging the interior of the specular highlight. As the artist drags the circle across the object, the system sets the new direction of light by sampling the off-screen buffer representing the reflected viewing angle. The final design interface fits a BRDF to a constrained concept art created by the artist. This is a small extension that's built on the same appearance model. Here, the artist starts from a rendering as a base to develop their concept. The rendering is loaded into Photoshop, and the artist manipulates the rendering to create a desired surface finish. This concept artist uses various tools to simulate the various appearance properties of the metallic surface finish. They can use any of the Photoshop tools. Our system uses the resulting concept sketch and computes a least squares fit of the BRDF, aided by the lighting and geometry information from the original scene. Any adjustment made in Photoshop can be synced back by simply saving the changes. A new BRDF is computed in less than a second. This system will have fitting failures if the artist fails to make an image with lighting consistent to the original. It is hard to evaluate the interface because it is difficult to find subjects who have a working knowledge of the standard industry terms for describing metallic colors. However, we did perform an informal user study of the interface with students of automotive design program at the College for Creative Studies and some of the color stylists at Ford Automotive Company. The College for Creative Studies is one of the few schools that trains automotive designers. Here, you can see them sculpting a concept car out of clay that is going to be sprayed with metallic automotive paint selected with one of our tools. The feedback was positive. In particular, the participants remarked that the pictures on the mood board interface suggested better starting points for their color design and allowed them to use their own reference material to seed the design process. They found it difficult to find a particular color using the single color wheel available in the previous generation color design interface. Using the BRDF Tweaker to point at the surface and adjust the color travel was considered to be more straightforward than manipulating the BRDF curves of the old color design interface directly. We also work closely with some of the top designers and color stylists at Ford Automotive Company. Again, the feedback was very positive. Current BRDF design systems do not leverage the unique creative skills of color designers. We presented a simplified metallic appearance model that allows us to create 3 color design interfaces for color stylists, including a virtual mood board, a BRDF Tweaker, and a Photoshop interface. Also, I'd like to mention that I find working closely with creative people as a very rewarding aspect of my research. Color science and imaging science has a symbiotic relationship with the creative world. Although color technology powers many creative industries like fashion, automotive, product, and packaging design, It is the designers that are able to apply color and imaging in such a way that makes people passionate about products. By considering their unique skills, we can make tools that leverage their abilities to the fullest. Thank you.